This is the combined Paper 2 revision video for sets 1 to 3. So the first topic we did was forces. In forces, you need to know what the difference between a scalar and a vector is. A scalar has a magnitude and no direction, and a vector has a magnitude and direction. You usually draw vectors using an arrow. The most common scalars are speed, time, distance, temperature, those sort of things. And the most common vectors are force, velocity, acceleration, momentum, gravity. Scale diagrams must be drawn as it says to scale. You need to pick a reasonable scale. Make sure you note it down on your piece of paper and make sure you do arrowheads. Forces can be in contact with each other, which means that they must touch, like friction, air resistance, stretching or tension, and normal contact forces. Or forces can be not contact forces, which means they don't need to touch to feel the force, like magnetism, electrostatic, and gravity. You have to learn 3 laws about Newton's. Newton's third law is when 2 objects interact, they exert forces that are equal in size to each other and opposite in direction. Resultant force is when you summarize all the forces into a single force. The only thing you need to remember here is if they are on opposite sides, you do a take away, and if they are on the same side, you add them together. Resultant forces can make an object speed up, slow down, or change direction. Newton's first law states about what do resultant forces do. So if you have a non-moving object and you put no force on it, it will obviously stay stationary. If you have a non-moving object and you put a force on it, it will start to move. Moving objects with 0 resultant force continue in a straight line at steady speed. And if you are moving and you put a resultant force, you can speed up, slow down, or change direction. Remember, if the resultant force is 0, we can say the object is at equilibrium. I know you don't need to learn the equations this year, but do make sure you remember that work done is the same as energy, so measured in joules, and your distances must be in meters. Higher tier this bit. If you're going to draw a vector diagram, so there's an example, you need to think of a suitable scale. So 1 centimetre would clearly equal 1,000 newtons would be logical. Make a point of where you start. Draw the first force to scale. So 3 centimetres, 3,000 newtons. And this is where people go wrong. Your second force must be off the arrowhead of the first force. Your resultant force then will be the completion of the triangle. And you can then use the angle. You can either use your mathematical ways to do your angle, or you can just measure it with a protractor. Remember, you should have a protractor and a compass for higher tier in an exam of physics. Parallelogram method is also higher tier only. If you've already got 2 forces and you have to draw a parallelogram, you will need to open the compass on one side, put it on the other side, and draw an arc. Repeat, and draw your parallelogram. You then need to measure the resultant force, this one here, using your scale. Make sure you know what the scale is. Make sure you tell the examiner what the scale is. Okay, back to everybody now. Weight's a force of gravity. It's different depending on what planet you're on. Weight is measured in newtons, capital N for newtons. Mass is constant no matter where you are in the universe, and it's got to be measured in kilograms. Again, there's another equation there. All I'm going to focus on here is remember that weight and mass are directly proportional. If you double your mass, your weight will also double. Springs, this is a required practical. Make sure you know that the original length is a spring in its unstretched state using their ruler, and your extension is the extra bit. So to work out the extension, you do your stretched length, take the original length. They sometimes ask you about hazards. Remember, this could fall over. That's a good setup to draw if you have to explain this practical. The sort of things they're looking for in this practical, if that was the table they're asking you to do, is setting up your clamp stand, hanging the clamp, holding the meter ruler in another clamp, hanging 2 newtons, because that's what it says here, measuring the new stretched length with a ruler, calculating the extension, and repeating until you've done all the forces. The only thing that could be different is they might say use 100-gram masses. Don't call them 100-gram weights. So either use 2 Newton forces or weights, or 100-gram masses. There's Hooke's law. Again, you don't need to learn the equation, but do make sure you remember the extension is measured in meters. Hooke's law has a graph that looks like this. It's a straight line graph to begin with, showing it's directly proportional, and then it will reach the limit of proportionality. To find the limit of proportionality, the simplest thing is to put a ruler on and look where it starts to curve. At the end of the graph is where it breaks. Sometimes these curve upwards. It doesn't matter long as it starts to curve. Two more equations on the formula sheet. You shouldn't have too worried. What I would say here is make sure you square the extension if you're working out the elastic potential energy. Remember, the elastic potential energy equation is on the front of your formula sheet because it's a paper 1 equation as well. Okay, motion. You need to know that walking is 1.5 meters per second, running is 3, and cycling is 6 on approximation. Depends upon age, fitness, terrain, etc. Do make sure you remember 1.5 double, and that's the easiest way to remember it. They might ask you to compare them. So, for example, cycling is 4 times faster than walking. You also need to know the typical sound in air is 330 meters per second. They do sometimes do that in standard form, so just be careful with that. Distance, speed, time. You do this in maths, so you haven't got too much to worry about here. Do not abbreviate distance to D. Okay, very, very important. Just because you do that in maths, do not do that in physics. If you were doing this equation, I would do it as words as per the top of the purple section there. In a distance time graph, so the y-axis says distance, any diagonal lines is a constant speed, any horizontal line is stopped. If you have an acceleration, you may have a curve. You can use the distance time graph to work out speed by doing distance divided by time for certain areas. Higher tier here, if you get a curve, all right, you do need to draw a tangent. Normally the hint that you've got to draw a tangent is 1, they've given you a curved graph, and 2, they've given you 1 time to look at. So draw a triangle, draw it big, but not too big. So make sure you don't go too far off the line of best fit. And then just do your gradient, changing y over changing x. Okay, speed and velocity, I've just told you the vectors and scalars. The way we show that velocity is a vector is because you can have a positive velocity going one direction and a negative velocity going the other direction. It does not mean they are going at different speeds. They're just different velocities because the directions are different. Acceleration, change in velocity over time. The only difficulty here is you might have 2 velocities. Remember, change is your final, take your start. Velocity time graph, so you've got velocity on the y-axis here. Your diagonals are now accelerations if they're going up in gradient and decelerations if they're going down. Constant speeds are horizontal and stopped is at 0. Higher tier, you may have to work out the distance travelled under the graph. You just do areas of triangles and rectangles, like base times height over 2 for a triangle and base times height for a rectangle. Just be very careful. You line off the sections that you need. It might not be the whole graph. Motion in a circle, another little higher tier bit here. Triple, this is also in a space topic as well. If you are traveling in a circle, you are said to be accelerating, but your speed is constant. The reason your speed is constant is because acceleration is a vector, so it also includes a direction. So it's the direction that's changing and not the speed itself. There's resultant force again. This is one slightly more complicated. So you take away those 2 because they're opposite. And then these 2, you're going to add these 2 together because they're on the same side and then take away. So you're going to summarize these 5 forces into one force of being 2,000 newtons forwards. With it being a vector, there should be a direction that goes with it. Newton's second law, FMA. The thing that you need to remember is acceleration and force are directly proportional. So you double the force, you double the acceleration. But acceleration is inversely proportional to mass. So if you double the mass, you're going to halve the acceleration. Okay? There's Newton's third law again. So 2 opposites interact, the forces are equal in size and opposite in direction. Inertia is about a tendency that an object will remain in its existing state, so either uniform motion, constant speed in a straight line, or still, unless it's changed by an external force. It's not a value, it's a tendency, it's a likelihood it's going to happen. Linear air track, I think, is one of the hardest ones to explain, but do just make sure that you'll need to measure the distance the object's got to travel, get the times from the light gates. Light gates are attached to a computer, so they can get the times automatically. You can then work out the speed. If you know the speed, you can work out using many different equations for acceleration. Terminal velocity, make sure you are aware that weight never changes, or the force of gravity. At the beginning, only weight acts, so you accelerate downwards. As air resistance starts to increase as your speed increases, eventually air resistance increases until it balances weight. You have then reached terminal velocity. Remember, terminal velocity is the maximum speed an object can travel with equal balanced forces, a resultant force of 0. That's what it would look like. So speed increases, terminal velocity is flat, speed decrease when you open the parachute, weight never changes, and then a new terminal velocity here with the parachute open, and then you land. Thinking distance, remember, is a distance you travel whilst you think about braking. So it's distance you travel whilst your human reaction time is being taken into account. This is going to be affected by anything that affects your human. The 3 favourites for me are alcohol, drugs, and tiredness. They are always accepted. Distractions are sometimes accepted. Speed is never accepted as an answer to increase the thinking distance because speed affects both. Braking distance is a distance you travel whilst your brakes are on and you're skidding. So again, my favourite answers here are like snow on road, ice on road, rain on road, reducing friction, or worn tyres and worn brakes, again reducing friction so you skid further. There are a few others on there, but I suggest you stick to my 2 favourite reasons because those are the ones that are always accepted. So when you're working out stopping distance, this equation will not appear on the formula sheet. You just got to remember it's the thinking distance plus the braking distance. Remember, if someone's drinking alcohol, that will increase their thinking distance, but it will have no effect on their braking distance. But it will increase their stopping distance because you add those 2 together. This is on the formula sheet and it was always on the formula sheet. A number you should be aware of if the acceleration to gravity is 9.8 meters per second squared. Always put the numbers in the equation first because you get a mark for that. Work out the side you know everything on. So you'll either know these 2 velocities or you'll know A and S. And then rearrange at the last moment. Make sure you give your answer a unit. If you don't know what unit to give, have a guess. Because if every answer in paper 2 requires a unit. Momentum, so this is higher tier only. If an object has momentum, it will have more mass and more velocity. An object has to move to have momentum. When you multiply your mass and velocity together, you can get the momentum, used to be called pulse, hence the symbol P. Remember, velocity can be plus or minus depending on direction. Remember, if you have a collision, the momentum of the balls collectively added together is equal to the momentum of the 2 objects afterwards. That is called the law of conservation of momentum. They might ask you why it's not 100% true in reality. You've got to think about resistive forces. You've got to think about friction, air resistance, and all those other factors. If you are triple, you take this further into conservation of collisions calculations. Okay, waves. Make sure you can label a wave. Remember the wavelength between 2 matching points, and your peaks are at the top, your troughs at the bottom, and your amplitude is between a peak and the undisturbed position, or a trough and the undisturbed position. So basically it's the half the height of the whole wave. And make sure you remember that the lambda symbol is symbol for wavelength. Don't use W. And frequency, remember, we always feel sorry for frequency because it hurts Hz. Time period, again, this is one that was always on the formula sheet prior to you getting the big formula sheet. So just remember that time period in seconds is 1 over the frequency. If you rearrange that for frequency, you do 1 divided by the time period. A lot of people think it's the time period times 1, which it is not. If it's in a triangle, the number 1 would be at the top. Ripple tank. Okay, ripple tank sounds harder than it is. Remember, when you've got the ripples, you can use a meter ruler to measure across as many waves as there are. So let's say there's 10 waves. Measure the length of all 10 waves. Divide it by 10 to get the wavelength of 1 wave. For the frequency, you count how many waves are passing a point in, let's say, 10 seconds using a stopwatch. And you divide by 10 to work out the frequency of the wave. You can then multiply those 2 values together to give you the wave speed. Waves on a string is very similar. but rather than you having ripples to count, you've got a string that's vibrating up and down. The easiest way to do this is either make it into a stationary wave or take a picture of the wave with a ruler in place. The ruler can then be used to measure the wavelength, and the frequency, you can either get it from the vibration supply or count how many vibrations there are in 10 seconds. Again, frequency times wavelength gives you wave speed. Do you remember that waves all transfer energy and not matter? So, for example, in a water, it's the wave that travels and not the water. They can be categorized into mechanical and electromagnetic. Mechanical need a medium, a substance, to travel. Electromagnet does not. Electromagnetic, remember, all travel at the speed of light in a vacuum. Transverse waves, oscillations or vibrations if you prefer, are perpendicular to the energy transfer. The example for transverse waves is every wave that you've done this year except sound. Longitudinal waves, all right, have oscillations or vibrations parallel to the direct energy transfer, and this is sound waves and ultrasound. You do need to be aware in a longitudinal wave that we call the squashed together bits compressions and the stretched out bits rarefactions. If you wanted a wavelength from a longitudinal wave, you'd just measure from the middle of a compression to the middle of the next compression, or the middle of a rarefaction to the middle of the next rarefaction. Okay? Sound waves, you do need to be aware that sound travels fastest in fastest in water, because it needs the particles. So fastest in solids, actually, if you want to be really specific. All right, because it needs the particles. Light does the reverse. Light travels fastest in vacuum because it doesn't need the particles. You do need to be aware that the speed of sound in air is 330 meters per second. The denser the material, the faster sound can travel because it needs those vibrations. The electromagnetic spectrum are all transverse. They all transfer energy. So you ever ask for similarities of electromagnetic spectrum, that's what they do. They're all transverse. They all transfer energy. They all travel at the speed of light in a vacuum. You should be aware that the longest is around 10 to the 3 meters, and the shortest gamma rays are around 10 to the minus 14. Just because gamma has a shorter wavelength and higher frequency and higher energy does not mean it travels any faster. All the waves in the spectrum on the next slide travel at the same speed. So you need to know them in order: radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. These are the long end. This is the shorter end. I did give you a mnemonic to remember it. Random monkeys in violet underpants exterminate gorillas. Remember, long wavelength, low frequency, short wavelength, high frequency. Make sure you know the uses. All right, radio waves, your radio signals, and your normal TV signal. I mean terrestrial TV, 1, 2, 3, 4. Microwaves is your satellite TV, sat-nav, satellite communications, cooking food, mobile phones. Mobile phones do not use infrared, no matter what your mobile phone company tell you. Infrared is anything that glows red in your cooking, in your kitchen, so your grills, your toasters, your halogen hobs if you've got one of those, remote controls, infrared cameras, and electric heaters. Visible light, so we can see. Fiber optic broadband is transferred via visible light. Ultraviolet, energy efficient lamps, sun tanning. Also, you can use the banknote forgeries. X-rays images bones. Gamma rays can be cancer treatments like your radiotherapy. Dangers, okay, your microwaves and your radios could heat you up, but pretty much not dangerous. Your infrared could burn you. Think about a toaster, it gets hot. Your visible light could blind you, so not looking at the sun. Your ultraviolet could cause skin cancer, not just cancer. Be very careful there. And ultraviolet and gamma rays can mutate healthy cells, which could turn cancerous. This little bit is higher tier only. If they ask you about how radio waves can produce electrical circuits or electricity, talk about that you're absorbing the energy at the beginning, making the electrons vibrate, inducing or creating an alternating current. And what's important is it's the same frequency as the original wave. So the transmitter transmits, let's say, radio 1, and your receiver also receives radio 1 at the same frequency. Okay, you all need to know about optical fibers. They carry light or infrared. The important thing is they cannot escape the fiber. You use them because they can carry more information. That's why fiber optic broadband is faster than normal dial-up or normal Wi-Fi. but it's also secure. Because the light can't escape the actual beam, then it stays in the fiber, making your information secure. High energy electromagnetic waves, these are the ones that have more of a danger to the human body. You need to make sure you know the radiation doses in sieverts. Basically, they might ask you, like, if a X-ray at a dentist gives you 2 sieverts and a pilot has 20 sieverts a week, how many X-rays can you have at a dentist till you get the same amount as a pilot? So just basic maths there of a comparison. Do make sure you are aware where gamma rays come from. So from paper 1, they come from the nucleus of an atom. X-rays and gamma rays are both ionizing. That's a word we used in paper 1, which means they can mutate cells and can cause cancer. X-ray are transmitted by soft tissue. They pass through it. That's why they don't show up on an X-ray. And absorbed by bone and metal. That's why they show up white. Ultraviolet light can prematurely age your skin and can increase the risk of skin cancer. Both gamma rays and X-rays give you a small dose, which could cause cancer. So to reduce this, they tend to give you lots of small doses on a tumour at different angles. You can see it here. So then the tumour is getting a high dose, whereas the rest of your body is getting a much lower dose. People who work with X-rays and gamma rays often work in rooms lined with lead, because lead will absorb stray X-rays and stray gamma rays. Infrared is heat radiation. Every object emits infrared radiation. The hotter it is, the more it emits. Infrared can be absorbed, transmitted, emitted, or reflected, but the amount that's emitted, reflected, and transmitted depends upon the surface size, colour, and texture. A practical to do with this is Leslie cube. So Leslie cube is a cube with 4 different sizes painted with different colours. You place it on a heat-proof mat and fill it with very hot water, kettle used. Use an infrared detector at the same distance from each of the surfaces, and you note down how much infrared is emitted. We would show our diagram as a bar chart because the independent variable being a colour makes it categoric. The results you should find is matte black, so that's dull black, our best emitters and best absorbers. Then every other colour, so greys, pinks, whatever, till you get to white, which being nearly the worst emitter, and silver is the worst emitter, worst absorber. Do remember, just because they're the worst at it doesn't mean they don't do any absorbing and any emitting. They do, just not as good as black. And make sure you're aware that shiny surfaces are good reflectors. Refraction diagram, this is in triple and combined. Make sure you're aware of the labels. So instant goes into the block. Angle of instance is the angle there from the normal, dashed line. Angle of refraction is underneath, inside the block. Refracted ray is that ray there next to the normal for that angle. And the emergent ray is the one that emerges out of the refraction block. Refraction happens because light has travelled from a different medium, so it changes its velocity and its direction. The opposite to sound, when solids have light going through them, the light travels slowly because it's more dense, and in gases it travels more quickly. When you enter the block, the light will go towards the normal, making the refraction angle smaller than the instant angle. When it leaves the block, it bends away from the normal, making the angle bigger. The way I remember it is Tagaga. It goes towards the normal between air and glass and away from the normal between glass and air. So Tagaga. If waves enter along the normal, no refraction is happening. It carries in a straight line. Wavefront diagrams. So if it was a refraction diagram with wavefront lines, if they enter at an angle, you will get refraction. Closer together will give you a slower speed. Wavefronts travel slower in shallow water. Okay? And finally, magnetism. Make sure you're aware that magnets have a north and a south pole. That is where they are the strongest magnetic field. Magnetic fields go from north to south. Look at all these arrows going north to south. I used to use the burger analogy for the shape. Okay? They're stronger at the pole because the lines are closer together. Look how close these lines are together compared to these ones, much further apart. So stronger at the poles. You may have to describe a permanent and an induced magnet. So a permanent magnet has a permanent magnetic field all the time. An induced magnet has a temporary magnetic field when being close to a permanent magnet. We did this experiment. How many paper clips could we stick together? Remember, if it's attracted to a north, it must be a south, and then that end must be north, attracting that south, and so on and so forth. Remember, when we took the magnet away, all the objects fell straight away except the steel paper clips, because the steel paper clips lose their magnetism really, really slowly. Okay? Whereas iron, cobalt, and nickel lose their magnetism really quickly, so they fall from the permanent magnet. You could be asked about 2 practicals. It's not required practicals, but they are required in description. If you have to show how a magnetic field is around a magnet, you can either describe the iron filing experiment. So magnet, paper on top, sprinkle your iron filings, observe. If they ask you to plot or find the direction of a magnetic field, you will need to do the plotting compass experiment. The plotting compass experiment has a magnet on top of a piece of paper. You move a compass around the magnet and you note down the arrow of the compass, and then you join all the arrows together to work out which direction the magnetic field is going. So there it is, and you can see it's stronger because you've got loads of iron filings being attracted to it. Remember, the Earth has a magnetic field because we believe the center of the Earth is iron. If a compass is not near a permanent magnet, it will point north, trying to find the Earth's magnetic field. If you move a compass near a magnet, the magnet will be stronger than the magnetic field of the Earth, so it will attract to it. Fleming's right-hand rule, both higher tier and foundation tier need to be able to do this. This can show you the direction of the magnetic field. You hold a pen or pencil in your right hand with your thumb upwards. Your thumb will tell you which direction the current is going. The pen is the wire, and your fingers show the circular direction of the field. If your pen is coming into the page, you will notice your fingers on top are pointing that way, as per these arrows. If your thumb is pointing towards you, coming out of the page, then your arrows will rotate. Magnetic fields are circular when looked from above down a wire. If you make a wire into a solenoid, that means you coil it. The reason we coil the wire is because solenoids are stronger and the magnetic field is uniform in one direction. To make a solenoid into an electromagnet, you will add an iron core or any magnetic material core. So iron, nickel, cobalt. You wouldn't probably use steel because remember, steel retains its magnetism. So when you switch the electromagnet off, it wouldn't drop it. We did an investigation for electromagnets. What you often find is if you want to make an electromagnet stronger, you can either increase the voltage or the current, or you can increase the number of turns on the electromagnet. If you want to know which of your electromagnet is north, if the current is going anti-clockwise, then it's a north, N for anti, N for north. And if it's going clockwise, it is a south. The field around a solenoid or an electromagnet looks exactly the same as the field around a bar magnet. Again, arrows going from north to south. You may need to know the motor effect. This is for higher tier now. So if you get current going through a wire and you place it into a magnetic field, it will experience a force. That force is called the motor effect. To work out which way that force will be felt, then you need to do Fleming's left-hand rule. Fleming's left-hand rule, your thumb is your force or your movement of the wire. Your first finger is your magnetic field, north nearest your palm and south at the end of your finger. And your second finger is the current, plus near your palm and minus at the end of your finger. You just need to bend your hand around, use your exam paper to move it around to make sure you get it into the right position. If you're asked to describe Fleming's left-hand rule, make sure you say they are perpendicular. If you want the wire to move up rather than down, then what you need to do is you need to reverse the current or reverse the magnetic field. If you want to make your force be bigger, you can increase the current, make the magnet stronger, or increase the number of turns. And the final bit, FBIL, they really like using this equation. It comes up most years. The unusual thing is magnetic flux density is measured in Teslas, capital T. Sometimes your lengths will be in centimeters, make sure you put them in meters, or millimeters. Millimeters to meters, divide by 1,000. Okay? Amps for current, and force, as with every force, is a Newton. But magnetic flux density is Teslas, capital T. Good luck.